Participation, every single person. Give it thumb up. Thumbs up. Everybody thumbs up. Okay, good. So imagine a sunny day. You're enjoying your time with your family, enjoying nice food, laughing. Then this 10-year-old boy approaches you, looks you up in the eye, and asks you, what is it that you do for work? Then you just say, oh, I work with transformers. Then all of a sudden you see the face of this kid changing, morphing into puppy eyes, as if you were about to give him a treat. And then it just clicks, it's like, oh, not those kinds of transformers. Well, just as in the mind of this 10-year-old boy, there's a preconception of what a transformer is. Most of the people outside of our industry, whenever they hear magnetics, they think about magnets. So that's why today we're gathered here, just to discuss different things. But one of them is to basically find out why our industry is called magnetics. So after this presentation or after this seminar, because yes, it's good to clarify, the idea is that all of us participate. You're gonna be having hopefully some fun. And if not, then at least you're gonna be having some competitive fun, because the key is participation. Participation. Thumbs up. There you go. So, and also we're just gonna talk about different materials, like basically the essential materials that we use in our industry. And the idea is to have an understanding of why they are used. Now, also, I'm not just gonna be the one speaking, because the idea is for everybody to learn something. So if there is any question in the middle of a slide, just ask the question, because that's how we're just gonna keep going and answering as we go along. If I see that the question is relevant later on, then I'll say so. Thumbs up? All right. So basically, to have a good understanding of magnetics, we have to create a mental picture of something that we cannot see. It is there, but we cannot see. And we're just gonna start with an electron. So an electron is an electric charge dot. So it is a dot. It is something that the naked eye cannot see, and even if you use microscopes, you cannot see an electron by itself. But so we're just gonna assume there's a dot. Whenever you have electrons flowing through a line, whenever you have this, there will be current. So whenever you have a net movement of electrons, or those charged dots moving, you're gonna have a current, always, no matter what. Now, one of the things to keep in mind is that whenever there is current, there will always be a magnetic field. So let's do the thumb up again. And remember, it's the right hand. So this is called the right hand rule, because whenever there is current, you can figure out how the magnetic field is moving based on your right hand with the thumb up. So if right now we point with our thumb in the direction of the current, so now pay attention to the way your fingers are curled. That's how the magnetic field is going to be around a wire. So that squiggly line, or that arrow, that revolting arrow, that's magnetic field. And that's how you can tell how the magnetic field is distributed. Now, this is just with one line of electrons moving along this particular case. Now, keep in mind, I mean, in this case, you may think of this as a wire, but in general, you're gonna have this whenever there are electrons moving, whenever. Now, what if we have two lines? Well, so if we have two lines, then there are different things to consider. First, how far those lines are from each other. So we are assuming that both of them are having current, therefore each one of them has a magnetic field. But if they are far apart from each other, there is no interaction. So it's just like having two magnets away from each other. But if we put them close together, then what's going to happen is that the magnetic field is going to intensify. You're basically doubling the magnetic field. But we also have to pay attention to the direction of the current, because if the direction of the current is opposite on each one of them, then they will cancel each other and there is no magnetic field. So in this situation, there's current on both, but there is no magnetic field. And now what happens if we just have that line of wire? So now let's say we have this line and we just change the shape of the line. So instead of having just a straight line, what if we loop it around? Well, what's going to happen is that the line itself is still going to have the magnetic field. So you're still going to have the magnetic field around the whole thing. But in the center, the magnetic field is going to intensify. On the outside, it's pretty much going to be the same as if you had any wire. But on the inside, it is going to add up. And that's what happens when you have a loop. So whenever you have a loop that is carrying a current on this, I wouldn't say specifically in the center, but we know that somewhere inside of that loop, the magnetic field is just going to be stronger. So that's how we get a stronger magnetic field. And then so we already know that whenever we stack things up, as long as the current is going in the same direction, the magnetic field is going to go up. And whenever we loop something, then the magnetic field is going to be stronger in the center. So if we want to create a virtual magnet, which is basically what we do in our industry, then what we do is that we have multiple loops and we stack them on top of each other. Because that way, we have the best results of a virtual magnet right in the middle of those loops. I mean, somewhere in the middle. Let's just put it that way. Somewhere in the middle. Now, the key is, and let's recap, the key is the shape, the key is the direction of the current, but also how close they are to each other. So it is very important that those loops are very, very close to each other, because the closer they are to each other, the stronger the magnetic field. So basically, if we have one loop, we basically have one size virtual magnet. If we put many loops together, then that virtual magnet is just going to grow. And that's how it works in our industry. And that's exactly the reason why we use a lot of this, to create loops, or turns, as we call them in the industry. Now, this is called magnet wire, and it's called magnet wire not because it's magnetic, but because it's used or utilized to create virtual magnets. Why? Because what's special about this wire is that the insulation is very thin. So having very thin insulation allows you to put those turns or those loops closer to each other, therefore improving that magnetic field. So now we're having activity time. Has anybody here never used a battery? Okay, good. So I'm pretty sure that none of you who have handled a battery has ever gotten shocked by it. Well, even if you put it in your tongue, actually, you will not get shocked. You will feel funny, but hey, well, it's important to make this clarification. So if I put my finger across this thing, nothing is going to happen. If I put probably 7 of these in series, then you're going to feel something. So why I'm pointing this out? Because you are going to peel that wire off and put it at the end, and you can just hold it with your fingers. Nothing is going to happen to you. Nothing is going to happen to you, all right? Now, you're going to feel that wire getting warm. So, yeah, just activity time. Whoever gets the answer first gets a reward.
How do you turn it, though?
Okay, look, participation, you see? Participation. You just got a card for that, mister.
Thank you. So we're wrapping the I don't know if that's good to have a card.
Participation.
Oh.
You just got a card because Adam just found the reason why we need this. So that is called a bobbin. If you don't have a bobbin, life is harder to making a virtual magnet. So, okay, for another reward, who can tell me 2 reasons for needing a bobbin? There are 3 reasons. There are 3 reasons.
To hold the wire?
General.
Structure.
So, which one?
Structure.
Okay, that's one.
To wind the wire up.
Yeah.
Okay. Any other reason? The first one to give me 2 reasons. We'll get this.
To mount on the board. PCB.
Okay, so what are the 2 reasons, Dennis?
To hold the cord.
To
hold the wire
to
down
wind
on the
the
board.
wire and to mount on the board.
All right, well, Dennis was the first one to give me the 2 reasons. There are 3 reasons. So here you go. So there are 3 reasons why. There are 3 main reasons why you will need a bobbin. And actually, you can stop right now. You're going to pause right now. You're going to pause. So there are 3 main reasons why you need a bobbin. So one is a structure, as Gretchen pointed out. But the structure is basically support for creating loops, right? So that's one of the functions. Structure to be able to create the loops or the turns. Now, Dennis pointed out the other reason is to put it on the PCB, and that's the reason for these little guys right here, which we call pins. So the bobbin will allow to have pin spacing that is consistent, so that when our customers get it, they will be able to easily drop it on the board. And there is actually a third reason, which may not be as evident right now, but is isolation. And isolation for what? Between the wire and the core. So there are 3 purposes or 3 reasons why we use bobbins in our industry. Structure, isolation, and we can just call it assembly. Now with this in mind, I'm going to hand out some bobbins, which is going to make this task easier for you. So let's just grab one bobbin and let's pass it along, please.
What do you need the bobbins?
Yeah.
Where do you get my
And so I'm going to, right now, okay, the first one to give me an answer.
bobbins look familiar to me.
The first one to give me an answer is gonna get another reward.
What is the question?
How many turns are required to attract a paper clip?
Okay.
So the way you're gonna do it is you have your battery, right? And please let me borrow this. So you are going to play with your wire. These guys right here, so these guys are easy to use to clip the wire. Now this other tool right here, which there must be like 4 or 5 of these on the table, these are make it easy to strip the wire off. So basically you don't put all the pressure down. So basically once you wind it, you strip it, and after it is stripped, that's what you connect to one of the terminals of the battery.
Just one?
And then you strip the other end and you put it on the other end. So basically you wind this thing on your bobbin, you have 2 stripped ends, and you connect one on each terminal of the battery. So right now, time is ticking. First one to give me an answer will get the reward. We're gonna move along. And if 8 minutes pass by and nobody has an answer, I'm gonna give you the answer and then we're just gonna keep going.
Where do you attract it to? The bobbin?
You will see it, as I said, because I'm going to ask, so if once you say you have an answer, you better have a demonstration for me.
Don't we all?
Oh, yeah, this is a separate tool.
And believe me, I know for a fact nobody has an advantage here. Not even Miles, who has one.
Will it work without stripped wire?
No, because it has insulation, so you need to have unstripped wire on the points of the battery or no current is going to flow. So remember, the idea is to use the bobbin for a structure. So let's use the bobbin to create the turns, the loops. And actually, Adam, so what you're doing, you don't need to loop it around the battery like that. All you gotta do is like, the easiest method will be to wind the wire on the bobbin and then have hanging leads. And then with those hanging leads, you're gonna just hold with your fingers on the battery. There is no need to make a fancy knot. Just by holding that wire down with your finger is enough to have enough current and create a virtual magnet. So we're creating virtual magnets right now.
Is there the least number of winds or just?
As long as you give me a number, I'll be satisfied. The first one to tell me how many turns are required to attract that paper clip will get the reward. And I know everybody here is competitive, so the idea is to have some fun, learn, comprehend our industry. So Gretchen, so like that's a great idea what you did there, but remember one of the key concepts is that those turns have to be very close to each other. So that's why I gave that bobbin, because the bobbin will make it a lot easier.
I need a clamp.
I'm gonna give you a tip. It's way, way more than 10. Hey, you have enough wire right in front of you.
My fingernail doesn't work. I know for sure I get fire on if I work in them.
Is it supposed to just pull the paper clip towards it?
Yep, that's what it does. Without touching the paper clip, it will just attract it. And so just put, one easy way is, well, I'll suggest you make those leads longer. I'll suggest you make the leads longer because you wanna have it hanging, and then with one finger just hold it down like this, like that. So you hold
One on one and one on the
you
other.
hold it that, and then the other there. Yes. Yes, Mr. Coin.
30 turns.
30 turns. Show me.
He just made up a number.
No, you're touching the paper clip with your hand. I need to see that paper clip moving on its own because of the virtual magnet you just created. You have enough wire in front of you.
Yeah. Why not?
So you're gonna have to terminate on pin number 6.
No, it's not enough wire. It's way more than 10.
My suggestion is don't terminate it on the pins. Leave the leads long enough. I'll say leave them at least 6 inches long, each one of them, and that will make your life a lot easier to connect into the battery.
Really?
Ooh, I'm already seeing some possible winners.
Yeah, it's got a lot of wire on there. Making it work. This looks good over there with that.
Does that have to be completely stripped or just showing some?
As long as it is showing some, it should be enough. But the more you strip it, the better. So let me see. Yeah, that's definitely enough. Just make sure that that's the part that you. And actually, I mean, I did this myself before I gave the task to you. So if you wind it first and then worry about stripping after you're done with the winding, it's a lot easier. So 150 turns will definitely attract the paper clip. If the battery is used up a little, then you will need something closer to 200 turns. But yes, that's the answer. I like the analogy between energy and water. If we were to have a cup and we want to fill this cup with water, I am pretty sure that none of you are going to think, okay, I'm going to fill this cup with water. None of you are going to have this mental picture. Well, that's the least of the ideas that you will have to fill that cup with water. You don't use a geyser. Why? Because the water is all over the place. It's going to be very difficult to catch it. Instead, what you're going to have is a controlled source, something where you can control the flow of water. There's a channel, there's a conduit. You know where it's going to land. So if we have a loop, all we gotta do is curl our fingers in how that current is flowing, because remember, the current is gonna flow in the same direction for every single loop, every single turn. So if you loop your fingers or curl your fingers in that direction of the current, then the thumb up is going to give you north. That is going to be your magnetic north. So let's say if the current is flowing that way, we are going to curl like this, that the thumb is up. So that's your magnetic north. If it is rotating the other way, it's the opposite. Now, the problem is that this magnetic field right now is just like having a geyser right there. I mean, the energy is all over the place. There is no control over that energy. So how do we utilize that energy? Well, what we do is that we use a pipe. Plain and simple. We implement a pipe to give a channel for that energy. Therefore, we know where it's going to be and how much there is going to be, and then we can put our cup. And this is why in our industry we use cores. So we use cores as a means to create a channel, a conduit for that magnetic energy, and we also utilize the core as a means to hold it together, and that way the system or our parts are more efficient. So that's all it is, a conduit to channel and control that magnetic energy. Sure, go ahead.
Is it safe to say it's harnessing the energy too and holding it?
You can say it is harnessing, because what you are literally doing is whatever magnetic field you're creating in the loop. So this is your source right here. The source is right there in the middle. Remember, it is strongest in the middle. Yes, you're gonna have something here and here, but it's gonna be strongest somewhere within the loops. And so Jim is correct. You are going to harness, because you're going to grab it from the source and distribute it around. And for that, you just got a reward. So that's what the core is doing. Now, having this in mind, activity number 2, another reward. So now we're gonna have exactly the same activity that you had before, but with cores. So this core fits nicely around that bobbin that you have in your hands. So whoever gives me the least number of turns required to attract the paper clip using the core, yes, please pass it along, then gets the reward. It's the same. Actually, we have more bobbins, so we can just utilize this. So maybe you help me around here. I'll start from the other end. Yes. So here we go. You got a brand new bobbin right here. That way you don't have to play with it. Oh, by the way, what you will do is that you wind first and then you put the core around. That's exactly how we do it. So
Is this right on this?
yes, that's basically how you do it, yes. But remember, the one who gets the reward is the one who tells me the least number of turns required to attract that paper clip using the core. And time is ticking. So my suggestion, Gretchen, put the core the other way around.
Okay, like that?
No. Take it out and put it from the pin side.
Okay,
There you go. And then try to attract it from that end.
okay.
Yeah, so what I was telling Gretchen is that it will make it easier for you if you insert the core from the pin side. If you insert it from the pin side, I mean, either way is fine. Either way is going to work. Yeah, do it the opposite. The opposite. Yep, flip it. There you go. You got it. Yes. And when you are going to attract the paper clip, you attract it from the end, from the open space. Okay, Enzo got it.
Moving too.
Enzo got it.
40.
Oh, nice.
40.
Okay, remember, the one who gives me the least number of turns is the winner. This time is still going, and I can tell you exactly, time is, we have about 3-4 minutes left. It's fine. You can just unwind it, and you don't have to even trim it.
Oh, really?
Oh, yeah. So you release some out.
But so far, Enzo was the first one. He's the winner so far.
How many turns was it?
I need to
Look at Dennis.
Can I get a stripper, please?
Ah.
You're not gonna find one here. Too early for a stripper? Delete that. Put that in the outtakes. That'll be the funny outtakes.
10?
The bloopers.
I felt warm. It's getting warm, but
It's getting warm.
Oh, Enzo, stop it. I beat you. You know it.
40. 30, sorry. 30. Look. 26. 30.
Still getting movement?
Yeah.
The 30?
Well,
I wasn't. So 30, you get movement. So Enzo, you get 30 moving? Fine. So now we have to do less, right?
No.
You're giving away your secret, Enzo.
I know, yeah.
Mine's warm, but it's not moving. I don't have more water.
20.
Getting movement at 20.
show me.
Right here.
Show me.
Look.
I got my hand.
My hands are sweating now. I'm gonna get a short circuit here.
Short circuit.
Look.
So make sure that doesn't short, otherwise it's not gonna, yes, something like that. Yep, you got it.
See? It did lift it earlier. There.
There you go. Okay, Enzo got it. How many turns?
20.
Okay, Mr. Enzo is the winner, the happy winner.
Good job, Enzo.
Good job, Enzo.
So,
So much time with your core and then Marvin. That's why you
so
I think it's just because you work close to the lab.
the idea of this exercise,
Maybe my hands got wet and it helped to increase the.
yeah, sure. your energy was transferred to the core. So the idea of this exercise is for us to have a good idea that there is a magnetic field, but the big difference that without a core, you can easily need 150 turns plus, 120 plus. with the core, you can go as low as 20. Now, there are different variables. So like for instance, how charged the battery is will affect that. The more you utilize it. So as you notice, many people here make comments that it was getting warm. What you're doing is that you're wasting energy. You are getting the energy out of the battery, and instead of transforming it into a magnetic energy, you're transforming it into heat.
Andres, 15.
Well, I'm actually surprised. So when I did the test, I guess I have used the battery enough that I got it to 25 turns. So I'm actually surprised that you can get it that low. But yeah, so that's the purpose of this exercise. We can stop. Thumbs up.
What about the size of the wire? Does it
I know,
Thumbs up.
Maybe
they're
it's not
28.
wire.
Okay, Helen just had an amazing question. So the size of the wire does affect the situation, but is not as evident. So let's put it this way. I got burned when I did the same test using 32 gauge, and that's why I didn't bring it. It will become a hazard. Yes, you can get burned. So the thinner the wire, the hotter it's going to get because the more energy you're wasting. So basically, to utilize the most energy would be a bigger wire, but I also wanted to bring a wire thin enough to be able to handle easily. So yes, the size of the wire does affect. Now, when we're building our parts, then you have other constraints. Yes, you want to use the biggest wire, but how much can you really fit in a specific bobbin size? So that's the kind of situations that you encounter. Good for you. You can keep playing. All right. So who can give me an answer? Why our industry is called magnetics?
Because of the magnetic field that you create by winding the wire around the bobbin.
Here you go, mister. You got it. Okay, and now we know why we use so much wire, correct? So, and the reason why we use magnet wire, not because it is magnetic per se, but because it was designed with thin insulation so that you can group those loops and create a stronger magnetic field. Also, the bobbin. So this is a quick recap. We're just recapping right now. The bobbin, three main functions. One of them is the structure, which creates a shape for your loops, for your turns. Sometimes you have it round, like in this bobbin, the one you had in your hands, or sometimes you can have it kind of a squarish. It doesn't matter, it's still a loop. It is still an enclosed loop. Now also isolation. The isolation is between the core and the windings, so that your windings are going to be sitting on the structure right there, and your core is right in the middle. And if you're wondering why, well, let me just make it more evident like this. So your wire is like this, the yellow one is the core, and the reason why you want isolation is just for electrical safety. Is not because it's going to affect the magnetic field or your virtual magnet or anything like that. It is only safety. You have the wire which conducts electricity, and it turns out that the cores also conduct electricity, so you don't want to have a short circuit. That's the reason why we use bobbins for isolation purposes. And then you also have assembly, which is provided by the pins. So we can think of it two ways. It eases or simplifies assembly on our end because it provides means for connecting those flying leads to a fixed location, and also assembly on the customer end because they are going to get a part that is consistent between pin-to-pin spacing and just ease of insertion into their board. And those are the three main functions for a bobbin. And the core. So the core is a means to channel that magnetic energy and a means to control it, a means to store it. In other words, it's a means to manage the magnetic energy. And what's important is that a core needs to be made out of one out of 3 materials. So I'm not going to go into details, but I'll say there are very fancy materials that nobody in the industry uses but NASA. So there's no need to discuss that. But any other core will use 1 out of 3, either iron, nickel, or cobalt. Out of those 3, cobalt being the most expensive. So why is that required? Because in order to channel the magnetic energy, it needs to be magnetic. And those are the only 3 materials that are magnetic in room temperature and above. So that is why you will have 1 out of the 3, or a mixture of the 3, or you can have one of those 3 mixed with some other materials. It doesn't matter, but it has to have at least 1 of those 3. And that's what makes a core. And in Premier Magnetics, the simplest part you can have is a toroid, which is this donut-shaped core and wire. And something particular about these toroids is that most of them will have a coating on them. So the coating, the sole purpose for the coating is to provide the isolation. You could have it without the isolation, but it is necessary when you want to avoid any hazards with electricity. So the coating, the epoxy coating, the parylene coating, plastic coating that you can have on the toroids is for that purpose, for safety, isolation. And then the shape itself helps in the structure, because if you cut it, and then your cross section will be kind of a squarish. Yes?
I got a question. I'm a little confused. Because the whole purpose of the core is you're gonna wind up the wire around the core, right?
Correct.
So why isolation if you need the electricity to flow through it?
No. Electricity is not flowing, it's magnetic energy. Remember, you're creating from electricity, you're creating a magnetic field.
That's what I meant, the magnetic field.
And so the core, the only purpose is to control the magnetic energy, not the electrical energy. You don't want a direct electrical contact between the windings and the core, because it can create a safety hazard. So transformers, one of the key uses or functions in any electrical system is isolation to prevent humans from getting shocked. Because you're dealing, for instance, you have transformers on the power lines that are dealing with 15,000 volts or 20,000 volts or 50,000 volts. And what they do is that they use transformers to go down from 15,000 to your house to a 120. And by the way, 120 will shock you pretty well. Don't even try to do it with your fingers. Because if you want to keep it safe, you better be under, I would say, 70 volts. So that's why I said, if we were to daisy chain 7 or 10 of these, you will get shocked. So it is for isolation. Yes, go ahead.
Can you just repeat? I know for us, we're using 3 major materials for cores, and typically for our stuff, we're using 2 different shapes for the most part, core style or toroids. And is the material the same for both of those different shapes?
So Premier Magnetics doesn't use that much cobalt. So cobalt, those are very expensive, usually custom-made cores. The advantage that cobalt has is that when you compare it to iron core, cobalt is way lighter. So it is going to be used in aerospace, and they're custom. So I will say, if I were to put a number, a figure, I would say 90% of what we use has iron. Maybe the other 10% uses nickel. And then it depends on how you process that iron or that nickel that will also make it different. So, Dennis, of course, is more familiar with most of you, or maybe Jim Coyne has also heard about the terminology, that powder irons and powder cores and laminations and all of this. That is not indicating so much the material, but is how that material is processed. So whenever you hear powder, what they literally do is that they grab the material and they grind it down, they make a powder out of it, and then they just kind of bond it together with glues or with pressure or with heat or anything like this. Yes?
And that's where you get the terms ferrite
And sendust, or is that
So-
different relationship?
Sendust is a trade name. So it is, I don't think it is proprietary, but it was used to name a particular material that is used as aluminum and iron and other things. I don't have the formula. Ferrite is also very specific on how the iron is processed. So I'm not gonna go into details, but since they brought it up, basically what ferrite does is that you have very tiny particles and they make them, so let's say that that red thing is your iron piece, and then after they grind it into very, very tiny pieces, then they put a coating around it. And so basically they create isolation, and that coating is basically oxide. So, and that's what ferrite is. You have grounded pieces with a coating of oxide. That's what makes ferrite. And then ferrite, not only that, but since they're so tiny, they're so minute, they have to gather a lot of it, and they usually combine it with other metals under high pressure, high temperature. And what you have at the end is just a ceramic, and just as any ceramic, like pottery that you have in your house, you drop it and it just breaks. It shatters. Yes.
Question.
So the three materials are iron, cobalt, and nickel.
You got it right.
And it doesn't really matter the shape, those are the same. So for the vast majority of our parts, whether it's E-core or toroids, it's gonna be either iron or nickel.
Yes, and I'll say 90+% are going to be iron. Nickel tends to be more expensive. Since I've been at Premier Magnetics, I have not designed a single nickel part. Maybe two, but it never even sampled those parts. Nickel is mostly used for RF. And actually, that's why I want to be clear why I say that at Premier Magnetics, this is our simplest part, a toroid shape and wire, is because we don't deal with a lot of RF parts. And in the RF world, the more you have like wireless signals and all of that, the cores are basically like as if they were not there. So then in that arena, in that region of the spectrum, you only have wire. So the simplest coil you can have is literally just a wire. And then they just specified like certain length, certain size, but you're doing the same thing. You're creating a magnetic field to be able to kind of utilize the electric energy into magnetic energy. Yes?
Yeah, I have a question. The toroid and the E-core with the coating, is the same material or different material? Because I've seen the different material on coating on the toroid versus E-core.
Yes, so the cord that you're holding in your hands right now has no coating on it. So that is ferrite. If you break it, it's going to look inside just like that. If you break this green core, then you can have different colors. One way of telling what kind of material it is, well, so if you break it and you see it brownish like that, like grayish, I mean not brownish, grayish, then it is an iron base. If you see it silver-like, then it's probably nickel, or you can have aluminum. So for instance, sendust, as Jim Coyne brought it up, it doesn't use nickel, but it uses a lot of aluminum and iron, so when you cut it, it looks silver.
Yeah, but my question is, I see like more on coating on the toroid than the E-core.
That's correct, because the coating or the isolation when you use an E-core is provided by the bobbin. So you only need epoxy on the cores when you're going to wind directly on them. When you're winding directly on them. And as far as the colors, it doesn't matter. You can have epoxy of any color you want. Most of the coatings that you see on any core is epoxy based. You can have other ones, but they just provide different things as far as temperature, isolation, voltage, and things like that. So, any other question? And at least right now, we know why thumbs up is with the right hand. So right hand is called the right hand rule. Whenever you're generating a magnetic field, you use the right hand. I didn't want to get too technical, because if I were to start explaining to you how transformers work, then we have to use both rules, the right hand and the left hand rule. But I'm going to make it simple. Right hand rule is for generating a magnetic field from an electrical current, and the left hand rule is the opposite, is to generate an electric current from a magnetic field. Any other questions? Okay, good. That's it. Thank you for your time.
That's it. Thank you, Professor.
Interesting.